I imagine that if you have more states that you are tracking, you may have like additional information to take decisions.
Yeah, but you are also increasing the size of your neural network, which is not necessarily good. Because then you have more things to learn.
Okay.
Like for example, in the states you can have, let's say you have a solar panel, right? So let's say that you, as a state, you can set the solar generation as a state itself, or you can use the solar radiation. So you shouldn't use both, because the solar generation is already correlated to the radiation.
So you need to select your states avoiding redundancies.
Redundancies, yeah.
Yes.
And then selecting states that will help you predict the reward.
Okay.
And then sometimes if you have a state that adds some information but it's not really a lot or really important, you might consider removing it.
Okay.
Like if you have, or the predictions, the prediction 6 hours ahead is different than 12 hours ahead.
And what are the set of actions that you have? Are those listed on the JSON file?
Yeah, here. Yeah, so the actions, you can see them here. You can select them here as well. The cooling storage and the domestic hot water storage.
The true or false here, like these are the two actions.
Yeah.
Or not?
In every building. So in every building you can select the actions. So in this building you have storage, cooling storage, which will be an action. It can go from minus 0.3 in this case.
But you do not have the hot water storage in this building.
In this building, no, but in this other, you do have it.
So
that's true.
So in the end, for this building, the actions that I have is to store the cool water or to use it.
Yeah.
Okay.
Yeah, and it's a continuous action. So it can be any continuous value from a negative value to a positive value.
Okay.
It's not discrete, yeah.
And based on my energy demand, that's how the decision is going to be taken to set this value. Okay.
Yeah, exactly. And you have it for all the buildings, these actions and states. So now if we go to the data file and to some specific Okay, so yeah, if we go to the data folder and some specific climate file with all the data from all the buildings, we here also have a JSON file with the building attributes that we can open, and then we can see what are the characteristics of each of the buildings, including how much solar energy we have installed. So we can modify this if we want, and just reduce it or increase it for that specific building. And then also the features of the characteristics of the heat pump, the electric hot water heater, including the efficiency, and also the chill water tank, including the capacity and the loss coefficient. So the capacity is a function of the maximum energy consumption of the building for that year. So if the capacity of the chill water tank is 3, it means that it's sized at 3 times the maximum cooling demand for that building in that year. So if the maximum cooling demand of the building for 1 hour in that year is 20 kilowatts, then the chill water tank will be sized at 60 kilowatts hours if the capacity is equal to 3. And then we have the loss coefficient, which is how much thermal energy the tank is losing every hour, which in this case is 0.8%. So there will be some buildings that do not have domestic hot water, like for example building 3. So we see that it has no domestic hot water, and then in the data file the demand for domestic hot water will be 0. So then in that case, when we go to our file buildings state action space, we want to make sure that the action for that building for domestic hot water is false, because we don't need to take actions there, and that we only have a true for cooling. And then, yeah, I was discussing before how to select the states. So in general, in reinforcement learning, we want to select as few states as we can, but adding as much information as possible. So we want to avoid any states that might be redundant. So for example, if we have a building with a solar panel, then here we can potentially add a state that would be the solar generation. So we can add this as a state. But we can also add the solar irradiation as states, the diffuse solar radiation and the direct solar radiation. What we should not do is to add all of them. Like we either add the solar radiation or the solar generation. But adding all these states at once are just adding redundant information. And then these variables will be correlated into our neural network, and it will not be able to learn as well. So then, for example, if we have a set of 9 different buildings, and they all have solar generation, then we can either add the solar radiation for all of them, so we would need to add 2 more states, let's say diffuse and direct solar radiation. So that would increase the number of states by 2 for all the buildings. However, if we choose to select the solar generation as an action, as a state, then every building will have a different solar generation. So instead of just adding 2 states to our system, we would need to add 9, 1 solar generation state per every building. So it's much more efficient to just take the weather conditions as states, because they are the same for all the buildings, than adding an additional state into our system per building that we have. So it's more efficient to use the weather data for this purpose. Then in CityLearn, right now we are just running this for one particular building, but we can run as many buildings as we want. So for example, yeah, here, like we're only running building 3, but if I want to run more buildings, like building 1 and building 2, that's it? Yeah, the command, yeah. Okay, so now it is loading all the states from all these buildings. So now we can see that instead of having, I think it was 5 states from one building before, now we will have 14. And CityLearn is automatically removing any redundant states that we might have. So the weather conditions, it will automatically remove them. So now we have 14 states. So let's say I go to the buildings again, and for building 3, I add also the, I don't know, let me see. Yeah, let's say I want to add the day of the week as a state, and that I add it for every building. So theoretically, I've added an extra state for every of the 3 buildings. So the number of states should increase by 3. But since this is redundant information, because the day of the week is the same for all the buildings, it will be automatically removed, and the number of states only increases by 1. So then if I run this, it will automatically give me all the boundaries for all the states of the 3 buildings. And then this works if I do it for a central agent. So in CityLearn, when I define the environment, I can select here that I want to have a central agent that is going to control all the buildings, which means that it's going to take all the states and also all the action space. So we can see here the actions for all the buildings. So this is 3 buildings, but 2 of them have 2 possible actions: the domestic hot water storage and the cooling storage. And then the 3rd building only has 1 possible action, which is the cooling storage. So we have 5 possible actions. But now let's say that I don't want to have a central agent. Now let's say that we want to have one agent per building, and because maybe we want to share information and coordinate them with each other, like have some decentralized system. So we can just set this to false. Well, yeah, before, so when I take reset, then I will get, let me see. Yeah, so this is for the central agent. So if I take a specific action, I will only obtain one reward and one array with all the new states and everything, just as if we have one agent. But now I'm running this for a decentralized agent. So now we can check the new variable, which would be, so I can check this other variable instead of observation spaces, yeah? And then it will have one set of states for every different building in a list. So if I want to access one of them, I just have to access one of the elements in the list, and then check the boundaries for that specific building. And I can do that for all the buildings. And then I can reset the environment, and then I will get a list of states. So I can check the states of the first building, the second, and so on. So I will be getting everything as lists of things. And then if I want to take the actions, I will have to take them in the same way. This is the action for the first building, for the second building, and for the third building. So I will take them separately.
Are they two different time steps, the 0.3, 0.3? What's the list signifying?
Wait, which ones? Here?
Yeah, so in that first, yeah.
There are two actions? Or?
So are they two different actions?
Yeah, so it's the same time step. So this action is for storing cooling, and the second action is for storing domestic hot water.
Okay.
Yeah, so the action, we have two possible actions, two actions, and then within each action state, each action space, we can take a different value. Like, yeah, this will be storing more cooling energy and domestic hot water. Then this will be storing more cooling energy and releasing hot water. And then each of these lists will be the action for every building, which has two dimensions. Building 3, we said before, that had no domestic hot water. So it's only an action for cooling. One possible variable. And then here we can see that it will return also a list of lists with all the new states for every building. And then it will also return 3 different rewards, 1 reward per building, because this is a multi-agent system.
Is it possible to put a couple of buildings together as with a central controller and then bunch of other decentral controllers?
Mm-hmm. Yeah.
Oh, okay.
To implement, for example, the OpenAI stable baselines and these packages that are typically online, we can do it easily if we use a central agent. But there are not many for decentralized agents. So if you want to run your decentralized agent, you can set this option to false, but then you will probably need to hard code in PyTorch your own agent and do all the coordination in Python. It will be hard for you to use any packages that are already written.
How do you define the communication links between the different decentralized buildings here?
So you would manually need to write some code that will read. So when you take let me see.
So in this scenario, I think every building can talk to everybody else, right?
Yeah, so you will take you will take an action for all the buildings, and you will obtain the new states for all the different buildings, right?
Yeah, in the decentralized case.
In the decentralized case.
Yeah.
And then every building will receive these states into the actor network. And then the actor network will tell what the optimal actions are. But then, for example, instead of taking all that action at the same time, then you can set some order. You can specify some order in which the buildings will take the decisions. So maybe one building will input the states into the actor network, and then it will feed that action to another building, which might use that action as a state, for example. So then buildings might choose the action sequentially. So they somehow need to share that information and coordinate. So you can just write that internally by receiving all these values. You just need to write multiple agents that will share this information. And yeah, if we have it set it to true, and we just want to run all of them at the same time as a central agent, then we don't really need to do anything else. I mean, it's the same as for one single building. Like we just run this again, and it will run for 3 buildings or for as many buildings as we want. And then here we are using the soft actor critic method, which is an actor critic method that is probably one of the most stable ones and the best ones. But then if we want to try different ones, then we can go to the OpenAI Stable Baselines website. And here we can find different types of agents that we can test. So depending on the reinforcement learning agent, they can be well suited for this problem or not. So in the case of SAC, it is suited for problems with continuous actions and continuous states. But for example, DQN will only be suitable for continuous states, but not continuous actions, but discrete actions. So we need to pick an algorithm that can be used for this kind of problem. So one would be the PPO, which is the one that is on policy based, so it cannot really learn from historical data, but it's also pretty good. So if we want to implement it, we just need to import this code. You could even try it right now if you want. And then in the model where we had a SAC, the SAC, you can just write the PPO, and then make sure that you change the hyperparameters, because some of the hyperparameters that we use in SAC might not be used by PPO. And then here you can just input the environment. So instead of the card poll, you will replace this by CT-learn, and then input it here in the PPO as a model. And then you just write a model learn, and it will start learning. In the total time steps, you want to write the number of hours of 1 year multiplied by the number of episodes that you want to run, or the number of years.
So in the previous algorithm, do we have only one critic actor, one critic network?
In the algorithm that we're running, the soft actor critic, yeah, so in that one we are using, it's an actor critic method, and I believe it has 2 critic networks. Yeah, 2 critic. I mean, there's no difference. The algorithm is basically the same, and the critic networks are trained separately. We are just, instead of using the Q value of one network, we just get the Q value from both networks and find the minimum of the 2 and use that value. Yeah, that's to make it more stable. Yeah, and then some of these algorithms will also use what's called target networks. So for every neural network we will have a second neural network. I mean, for every critic, we will have an additional neural network that is used as a target, which means that instead of updating the network every time step, we will use the target network, which will only be updated maybe every few time steps. That's to add more stability. Yeah, I didn't go into much detail, just not to add too many neural networks to the problem, but just for you to know that when you look into some reinforcement learning code, you might see these target networks. So it's just basically like a copy of the actual network that is being copied every few episodes or smoothly. It's just to increase stability. Okay, so here we can see that so the green dots will be the batch size 50, and then the red ones 125, and the blue ones 300. So apparently here in the results that we have gotten, we want to be using a learning rate that is closer to 0.01, more or less, or maybe a bit less than that. And then use batches that are probably as high as possible in order to learn better. So the best return rates are obtained for the batches that are 300, and for a learning rate that is in this range. We also got a good value for the batch size of 125 and with a lower learning rate. So yeah, actually the size of the batch is related to the learning rate that we want to use. So typically the bigger our batch size, then we can use a higher learning rate. And if we use a different batch size, then we need to modify the learning rate if we want to find the optimal solution to our problem. And then the size of the different dots indicates the tau factor. It is a value that indicates how fast our updates are being made. So as I said, there are some target networks that are used for more stability. And what we do is to copy the critic network that we have in the target network. So the tau factor is telling us what percentage of the parameters we are using to update these networks, to copy the network. So for example, if the weights in our critic network, the weights in our network in a given time step, and then we have a tau factor of 0.1. That means that in the next time step, we will copy these weights into the target network using a learning rate of 10%. It's just to increase the stability of the system. So that's what the tau factor is for. It's similar somehow to the learning rate. So if you want, you can now try to implement PPO2, which you can find in the website of the stable baselines. So you can just import this and then use it. And here you can see the parameters that you can use. You always have the learning rate, which is the gamma, and here you might have some other parameters that you want to change. So I suggest you can modify the learning rate. I would say the learning rate, and maybe gamma too, a little bit. So the gamma factor you can reduce it, but no more than 98, and no more than 0.995. And then you can just run it in the computer. So you should see that it will run much faster, but it's also less sample efficient. So you will need to run for a higher number of years. So before you had set the number of years to 15 or number of episodes, with soft-actor critic, which is very sample efficient, if you use PPO, which is a non-policy method, then it will need to run for many more years to achieve the same performance. But every update of every year, it will also happen faster in terms of the computation load that you need to use in your computer. So you copy this. So now it should be running with PPO2. And if we want to change the parameters, we can just do it here in the model. Yeah, so maybe we can create the same table, but changing the gamma and the learning rate for PPO. Yeah, so you can select the learning rate that you want and the gamma that you want within this range, and then test the PPO, and then you should also increase the simulation time a little bit, the total number of time steps. So if before it was 15, you can set it maybe to 20 or 25, or maybe leave it with 15, but you can run it and then see how it should run faster than before. Like all the updates are being done faster, but then also the gain in terms of how fast the cumulative reward is improving, it will also go slower. So updates happen faster, but it's less sample efficient because it's a on policy method and not off policy. But it might also obtain like very good results. And
you just from the beginning, you know, what code we have to start,
yeah.
And then.
So we go to the website of OpenAI Stable Baselines. And then here we just go to the algorithms section and we open a PPO2. And then we just need to import the package, like a gym and then the PPO and whatever it is using. And then go to CityLearn, go to the example central agent. And then, let me delete this. And then here we have the environment that we defined in. So this will be used by the algorithm. So after this, we will import these packages. Oh, here, you can click in this plus. So here you can create as many as you want. And if you want to delete them, you can just press and then press the key D twice, fast, and you will delete them.
Press what, sorry?
D, twice fast, yeah. And you will automatically delete them. And if you want to run them, you just need to click inside and press Shift Enter, and it will run it. So when you see this little dot here, when it is black, it means that it's running the Jupyter. It's running something. If you want to stop it, you click here, Interrupt Kernel, and it will stop the cell that you are running. But everything that you ran before, it's still stored. All the variables and everything is still stored. If you want to reset all the variables, then you go to kernel, restart kernel. This will clean up all the variables that you ran. So if you click on restart kernel, then you will need to run again all the cells. So yeah, we run this, and then here in our model before we had the SAG, and now we just write PPO. And then PPO is not really using any batch size because it's not storing any historical information because it's as the SAC is doing. So you will not use any batch size, but you will still use the discount factor and the learning rate that you can modify. It will be set automatically to some default factors, to some default values, but you can change it. And then this value, model, learn, this is the number of time steps, and then this log interval. I mean, it's just how often you want the package to give you information about the performance. So when we run it, it's providing this little box here with information about our performance. So the lower this value is, log interval, then we will get this small window more often. And then this cumulative reward is not provided by the stable baseline package, but is provided by the CityLearn environment itself.
So I think I noticed that for PPO2 we need less hyperparameters, right? We don't need tau.
No, we don't need tau either, or the batch size. No. So if you want to see what hyperparameters you can modify, you can go to the website, and then if you scroll down a bit, you can see the class, and you can see here all the parameters that you can change. The discount factor, and the explanation for each of them. So in this case, I think we can change the gamma a bit and also the learning rate, which will...
Tau and the learning rate are the same thing, right?
Not the same thing, but they are somehow, there's some similarity because they are related to how fast we are performing the updates. Yeah, but there will be a different thing. So the learning rate is how fast we are updating our main neural network, our main critic network. But then in some implementations of reinforcement learning, they use this other target network that I didn't explain before, just not to make things very complicated. But it's used to increase stability. So in our slides, I show how everything is updated iteratively. We update the neural network, and then with this neural network updated, we can go to our equation and update our Q-value, and then train the network again, and so on. So all this happening, updating the equation and the network at the same time, might increase in stability. So what we do is that we update the equation with a second target network, with a target network. And then this target network is updated less often. The target network will be a copy of our critic network. What we do is that we copy it using a factor tau. So if our tau is 0.1, it means that every time step, we will copy our critic network into the target network using a learning rate of 0.1. Tau is like how smooth we are copying the critic network into the target network. And the learning rate is more about how fast we update the Q-values. So the lower tau, the less often, or we just update the target network less often, so we increase stability. But then learning happens more slowly. Yeah, and the learning rate also, if we make it slower, if we make it smaller, then the updates will happen more slowly. Yeah.
Can we go back to the Jupyter?
Yeah.
Please? Yeah, thank you.
Another thing that I didn't show yet is the reward function. So I mentioned that we have different costs that we can optimize, which is our objective function, and we can define them here. We want to optimize for net electricity consumption, peak demand, average daily peak demand, 1 minus the load factor, and then the ramping. So we define this our objective function, and then we feed it into our environment. So it should be here when we define the environment. So then after running it, so if we run environment and the method cost, it will return all these values. So all these values are normalized as a function of the performance of the rule-based controller. So if ramping is 0.82, it means that is about 20% better than the rule-based controller. If it's greater than 1, it means it's doing worse. And then the total is just an average of all of them. This cost is just for if we don't have any storage. So just for many different buildings.
What
1
does it
minus
mean?
the load factor.
Of one?
Yeah.
Okay.
Yeah, the thing is that we are trying to minimize all these variables.
Yeah.
So in the case of load factor, we are trying to maximize it. So just to minimize it, I just did 1 minus the load factor. Yeah. Yeah, it might happen that the peak demand value might be lower than the average daily peak demand. And this is just because maybe the peak demand for the whole year is smaller than the peak demand for the whole year of the rule-based controller, but the average daily peak demand is better. And then, so this is the cost function, but then we have the reward function. So here we can write So the reward function will obtain the electricity demand for every building in the district. We have two different ones, the multi-agent one and the single agent one. But basically the input will be the electricity consumption, the net electricity consumption for every building. And then we can just write whatever function we want in order to feed the reinforcement learning agent with it. So whatever we change here, and this is up to us, then when we go to the environment and we take an action with the agent, the reward that it will get, it will be after processing the electricity demand with all this function that we write here. Ideally, we want to write a reward function that will allow us to optimize our cost function. But this can be a bit hard, because then if we have 5 different costs and one is ramping, they might be very nonlinear, like ramping, for example. Ramping will depend on the past electricity consumption and the present electricity consumption. So it might be a bit hard to write a reward function for that also follows a Markov decision process. Because Markov decision process in theory should follow that which rewards only depend on the current state and the action you took, not on the previous states. But maybe you can find another function that can also help to optimize the cost function. So in this case, it could be a quadratic function. So we just find a virtual price that is proportional to the electricity consumption in the whole district. Make sure that is positive, because there might be some solar generation. And then we just multiply it by the energy consumption. So it's basically like a square function of the electricity demand. So if we want to minimize that square function, then the flatter the electricity demand it is, the more the reward function will be optimized. And then all these variables of peak load, the load factor, and all of that are all about making smoother and flatter the electricity consumption. So any reward function that helps to make our electricity consumption in the district flatter and smoother will also help to optimize the cost functions. So one of these reward functions is used if we use a central agent, and the other is if we use a decentralized agent. So the reward function single agent is for the central one, so it will only return one reward, which is the sum of all the electricity consumptions to the power of 2. And then in the multi-agent one, it will return a specific reward for every agent. So if we have 9 buildings, it will return 9 different rewards, as we saw earlier. And this is something that we should code internally. So the things that we can tune here are the hyperparameters of the agent, what type of reinforcement learning algorithm we want to use, then what states and actions we want to use for every building, and then also what reward function we want to use for our learning problem. These are all things that we can modify in order to solve a reinforcement learning problem on demand response. And then the more updates you want to make and the more buildings you run, then you will need much more time and computational power. Like it's already maybe taking like 5 or 10 minutes for a single building. So maybe for 9 buildings it might take closer to an hour or something like that. Oh yeah, another thing is if you have a GPU or a graphic card, then you can increase your batch size and make the updates into the neural networks in parallel with the GPU, which might speed up things. And as we saw here, typically higher batch sizes will work better because they are more stable, and you can use a higher learning rate, which should make the updates faster. So, but then also if we use a very high learning rate, it will take very long. A very high batch size, it might take very long to make all the updates. So when it was like set to 2000, then it would take a really long time. But if we have a GPU, this might not be a problem. You might be allowed to use very large batch sizes that will increase stability and that will allow you to use a higher learning rate. And you can still make all the updates faster because you can parallelize them. I think so far the PPO is not really doing better than the soft actor critic.
So Jose,
Yeah.
so since every time that we run the algorithm, we might get a different results, although they might not be too far from each other.
Mhm.
Is it safe to say that we have to run the algorithm a couple of times and then take the average or something to
Yeah,
make?
so in research in reinforcement learning, you will, to show the results, you will want to run the algorithm maybe 10 or 20 times,
Mm.
and then just display the mean and the standard deviation.
And how about on certain parameters? And we always have uncertain parameters from the environment. How can you account them in the algorithm and the learning? Instead of solving like a deterministic optimization, can we do like a stochastic optimization or something?
Yeah, stochasticity in the actions or on what?
Even consumers' behavior is changing all the time, and
Yeah, so that's perfectly fine. So as I mentioned earlier, the reinforcement learning agent is going to try to solve a Markov decision process. So it doesn't have to be deterministic. There are some transition probabilities. What needs to be constant is the probability of something happening. But that doesn't mean that if I take an action in a given state, the output should always be the same. But the probability of getting one outcome or another has to be the same. Yeah. So
if not that one is not the same, then we have to use different probability transition matrix for the Markov.
well, we don't need to. So this is all implicit. It's not that we need to explicitly write equations of the Markov decision process.
Right.
Yeah. We just need to make sure that the way we select our actions and states for our controller, we need to make sure that the environment is going to follow a Markov decision process if we use those states and actions. And then the probability might be. Oh yeah. Mm-hmm.
Oh, sorry, you complete answering that question. I was just going to ask a follow-up.
Okay. Well, yeah.
With the stability in terms of the environment and the Markov decision process, how does that work when you have multiple agents and they're really affecting the reward that someone else might get?
Yeah.
And what's your experience been of?
Yeah, so there is tricky. So if you have a central agent, it's no problem, obviously. But if you are using the decentralized multi-agents, then the problem is that as you say, it becomes non-stationary. So each agent is going to be seeing a moving target because your other agents that are taking actions are part of your own environment as a building. And they are taking different actions and learning different things, so it's really hard to learn anything. So that's why what the agents need to do is to coordinate and share some information with each other. So they need to share, for example, if you have 9 buildings, you might want to select some extra states that give you information on what actions the other buildings are going to take. And then they might take action sequentially. So let's say one building, the first one that is going to take the action, selects what action it wants to take. And then it tells the other buildings or the next building what action it took. And then the next building uses that action of the first building as a state for its own. So now it knows what the other building is going to do and what the environment is like. And then it can decide another action. And it can provide that other action that it has selected but has not taken yet, and can provide it to the next building as another state, and so on.
Do you think it just wouldn't work if you didn't do that?
That's a way. That's something I'm exploring yet, but I think that should make it easier to work. So what I'm trying to implement now so right now I've been focusing on the central agent, but I'm starting to code the decentralized agents, and I want to share this state, and also I think I will use as another state how far you are in the line of taking the decisions. So I think the state will be what action has the previous building is going to take, and then how far you are in the line of the decision making, which will give you information of how many buildings still need to take actions after you. if that makes sense.
Yeah. Thank you.
And then, and then regarding the transition probabilities, then the transition probabilities can indicate both uncertainty, because you might not have selected all the states that provide all the information, so you have some uncertainty there. And they can also be implicit in your system itself. Like maybe you have a stochastic system by nature. Yeah. And then in some reinforcement learning algorithms also allow you to take stochastic actions. So instead of under some given states you take a specific action, then the agent might just take different actions with different probabilities given those states. So that's also an option. Which is the other thing that I want to try. Maybe the buildings they can just, based on these states, take probabilistic actions. So they don't all take the same action at the same time. But if you have multiple buildings deciding if they are going to store more energy with a 50% probability, then maybe they will spread out a little bit instead of consuming the energy all simultaneously. So that's one option too.
In the results, what's that total stands for? Like we have ramping, 1 minus load factor.
The total is just the average of all of them.
And how do you normalize them? I didn't get that point. Because in per unit system, we use a base and we can compare with each other. But here you are saying that we can't compare peak demand with the average daily peak because...
Well, once they are normalized, yes, we can. But if we don't normalize them, how do you compare peak demand that is in kilowatts with the load factor that is a ratio between 0 and 1, you know?
Yeah. What about the peak demand and the average daily peak? Is it in kilowatts or?
Well, you could compare those two directly without normalizing them, yeah. But some other values you cannot really compare them directly. So we need to normalize them.
May we get that normalized factor anywhere?
Yeah. So it's not explicit. So CityLearn, what it does is to run a rule-based controller into the environment, and then that rule-based controller will obtain these costs, and then it will divide the cost of your agent by those costs. I can show you now.
Yeah, that would be great.
Yeah, so here is the cost method for CityLearn. So we find the cost for ramping, the load factor, the average daily peak, the peak demand, and all of that. And then we divide them by the cost of the rule-based controller.
All right. Okay.
So we find the ramping and we divide it by this cost of the ramping, and the rest the same for all of them. And then the cost of the RBC is found here. Yeah, this one. Let me see. Yeah, so when you call the cost function, if the cost of the RBC hasn't been calculated yet,
Okay.
it's going to redefine all the environment and everything, and it's going to run the RBC agent. And it's going to run it for the whole year. And then it's going to obtain the costs of the RBC that you can see here. So this is to compute the cost for the RBC. So it will compute the cost for ramping, for the load factor, and all of these costs. And then it will divide those costs of it will divide the cost of your reinforcement learning agent by the cost of the RBC to normalize them.
Yeah, so can we see these costs with which we are dividing, like self-taught cost, because it's not
yeah, I
visible
think you might
anywhere.
be able to see them actually. Yeah, so you can just type environment cost RBC, and it will give you the factors
Yeah,
of the
okay.
normalization.
Yeah, thank you.
Yeah.
Any other question for Jose? Okay, I think we don't have much time, maybe 2 minutes. If you want to add anything at the end.
Just thank you everyone for.
Okay.
For
And
coming.
yeah, I think it went pretty well for me, at least. Hopefully for everybody else. A lot of we got our hands dirty with all the codes, and many of us didn't know about the Jupyter notebook and how to work with it, and so we learned a lot. And also reinforcement learning sounds pretty interesting. So thank you, Jose. Please join me in thanking Jose for this.